Nyquist plot. It is another frequency domain tool that we'll use in control systems. What is it? It is a plot of some transfer function evaluated at S equals J omega as omega goes from minus infinity to plus infinity. And it's a plot in the complex plane. So if you have a transfer function, it's a plot like this down here. What transfer function are we going to use? We're going to use this loop transfer function, product of G and H, the forward path transfer function and the feedback path transfer function. That product will be the loop transfer function that the Nyquist plot will be a plot of. If you had a Bode plot, you could theoretically go to the Nyquist plot. I'm not going to go through that, but that's what a Nyquist plot is. Now, why would you want it? We can determine closed loop characteristics for all k that we put into that loop transfer function. Once again, we're evaluating closed loop behavior from loop transfer function, and especially to see what happens as you change the gain of that transfer function. So it's kind of like root locus and Bode, but we'll have fewer restrictions than the Bode plot. What can we determine from that? What can we determine? Closed loop characteristics, primarily stability, the number of poles in the right half plane, and theoretically the phase and gain margins. We talked about that with Bode plots. I'm not going to cover that in my course for Nyquist, but we're going to be doing these top two bullets here. It has fewer restrictions. We can look at all k, positive and negative. So it's unlike both Bode and root locus. The poles, both the poles and zeros of that transfer function, of that loop transfer function, may be in the right half plane. We don't require minimum phase. So again, it's unlike both root locus and Bode plots. And we don't have to have unity feedback, which is what I limited our Bode analysis. The other good news, or at least the way I taught it, we didn't have to sketch the Bode plot by hand. We started with a MATLAB plot of, we used MATLAB for that. And the MATLAB command is pretty easy. If this is your loop transfer function, here's your MATLAB code, whatever they call it. So for this transfer function, it did this Bode. So we're going to use MATLAB for that part. Then it gets into how do we interpret it. And what happens is every point on the real line maps to a k. Or you can say k maps to some point on the real line. You need to get a little bit used to interpreting this because each point on the real line literally maps to -1 over k. So you have to do a little bit of sort of backwards thinking. Everything in the left half plane maps to a positive k. Everything on the right hand side maps to a negative k. It's kind of backwards. And out at the infinities are where k equals 0. And here at the origin is where k equals plus or minus infinity. Again, it's kind of the opposite, because we have a reciprocal relationship and a sign change. So say, take a particular point on the real line, say this -1. That means -1 equals -1 over k, k equals 1. Take this point, it looks like 0.5 on the real line. That means 0.5 equals -1 over k. Solve that little equation, k equals -2. So here, k equals -2. To the right, it's somewhere between 0 and -2. And between this point and the origin, it's somewhere between -2 and -infinity. Similarly over here. Out here to the left of here, k is between 0 and 1. And here, k, in here, k is between 1 and infinity, and positive infinity. Now, here's the calculation. Here's the Nyquist criteria. Z is the number of poles in the right-half plane of the closed loop system. That will also give us whether it's stable or not. If Z is 0, the closed loop system is stable. P is something we can determine from the loop transfer function without even doing the Nyquist plot. It's how many poles does in the right-half plane does the loop transfer function. Get that just from the algebra of the loop transfer from its denominator. N is the thing we need the Nyquist plot for. The number of net clockwise encirclements of the plot at that point. I'll have to show you how we determine it. So we get N and P from the loop transfer function, but Z characterizes the closed loops. Point of this. Okay, so how do we determine that N? If you look at this theoretical Bode plot, there's 4 different sections of it if you go sort of from left to right on the real line. There's to the left of A, there's between A and the origin, between the origin and B, to the right of B. To the left of A, there is no Nyquist loop, so N is 0. Pick a point here. There's no loops, not surrounded by any loops, so N is 0. Pick a point in here and go out to infinity, sort of have an imaginary line. It's encircled by 2 clockwise loops. So N equals 2 there. Here, between the origin and B, it's surrounded by 1 clockwise loop. N equals 1. And to the right of B, no loops at all, N equals 0. And from that, you can take any point and calculate what it means for K. Here, on this segment to the left of A, pick any point corresponding to -1 over K. That's less than A, and A is less than 0. You said N equals 0 there. Do that little bit of inequality algebra, and that means no poles. Well, this is assuming P equals 0 here, so that Z just equals N because P is 0. Over there, that means the closed loop system is stable. And here's where it is, where that's true for what values of K. In this little segment, that means any point on there, -1 over K, is greater than A, but less than 0. And that was where N equals 2. Solve that inequality algebra. Any K greater than -1 over A. A is going to be some negative number, so K is a positive number. That's where you get 2 right-half plane poles, and the system is unstable. I won't go through the other 2 segments, but One place where my students had trouble was that inequality algebra, and you just have to be careful with it. You know, anytime you multiply or divide by a negative number, you need to switch inequalities. K is greater than 0 over here. K is less than 0. And over here on the right, K is less than 0. The trick to finding that N, for any point on here, just pick some ray off to infinity in whatever direction is convenient and count how many times you cross some loop in the clockwise direction. Out here, it's going to be 0. In here, it's like there's 1, there's 2. In here, I have a counterclockwise, so that's a -1. And here is a clockwise, that's a +1. It nets to 0. So you're counting net clockwise, and if it goes counterclockwise, that's a negative. Here, there's just 1 clockwise, so n equals 1 there, and out here there's no loop, so n equals 0. So that's starting Nyquist criteria and Nyquist plots. We'll do more later, lots of examples. And more of their videos.